let me show you how we can translate loops and traverse arrays. I'm going to show you, okay, 3 types of loops and how we translate them into assembly language. So let us start here with this first example, which is translating a while loop. Okay, so I have a while statement. Let us take a look at this while loop. I have, okay, so I'm writing here I is initialized to 0. So I is just an index, okay, which is initialized to 0. And while AI is not equal to value and I is less than an I plus plus. Okay, so this is my while statement. Very simple. Okay, and I would like to translate this into assembly. So here A is an array of integers. So we're using an array of integers, and each integer is 4 bytes in memory. So it's an array of words, okay, because each word is 4 bytes in memory. So 4 bytes per element of the array. So the question is, how do I translate this code into assembly language? You don't really have to understand what this code does. You can translate it in a mechanical way. In other words, you just look at the statements which are written in a high-level programming language, and you can translate it into assembly. This is exactly how the compiler does the translation of statements which are written in a high-level programming language into assembly. So you don't really have to understand the meaning of this code to do the translation. And in fact, the compiler never understands the code which is written, the program, which is written in a high-level programming language when doing the translation. It does it automatically. Okay, that's how it does the translation. Okay. So this is what we are going to do. All right, so let us. So tell me how you would like to translate this code.
Yes, can I answer?
Yes, definitely. Go ahead.
First, we have to define the I load immediate register, for example, S0. Then define the counter. I mean, loaded with value 0.
So what we have to do is that we have to use registers that exist inside the CPU. Okay. So you have to decide that, for example, which register is going to be used for I. Here you need to read the value. Let me use here, for example, my pen tool. Here I have to load the value of AI from memory. Here I need to implement this while by branching outside the loop to terminate the execution of the loop, and so on, right? So let us take it step by step. Okay, let us start here by initializing I to 0. I need a register, okay, for this index, for this variable I need a register. So I'm going to say load immediate, okay, like you said. I'm going to use load immediate. I'm going to use register T0, okay, for I, and I'm going to initialize it with 0. Okay, so this is simple. This is how we initialize I with 0. So I here is a simple, okay, variable. It is just an integer, and it can fit in a register. So therefore, we can allocate a register specifically for this variable I. But the array itself cannot really fit in a register. So therefore, the array must exist in memory. We must have allocated the register, the array in memory. Okay, so I'm assuming that already we have the array in memory. Already we have read the value of the array. It's not really shown in this slide. So we need to write, let us say, we need to write the code that will read the elements of the array, so we can ask the user to enter the elements of the array one by one, and we can store them in memory. Okay, can you tell me what this code is doing? Can you figure out what it is doing? So this while loop.
Only incrementing I, nothing else.
We are searching for a certain value?
Yes, we are searching for the value here, value. Okay, we are searching for this value. So if this value is not found, we increment I. If the value is found, we terminate, we exit this while loop. Okay, if you really would like to understand what this code is doing, we are really searching. This is just a very simple linear search algorithm. Just a simple while loop that's going to traverse the array starting at index 0. Okay, starting at I equal to 0. We are searching the elements of this array element by element until we find value. If the value is found at a given index I, terminate the execution of the loop, and I will be the index of the element where the value is found. Okay, in memory. If it is not found, okay, we reach I as long as I is less than n, which is the number of elements inside this array, we loop back. If I becomes equal to n, we terminate the execution of the loop because the array is indexed from 0 to n minus 1. Okay, so notice that here we have three things. Okay, we have A0 is the address of the array. I have A1 is n, and I have A2 is the value. Okay, so this is given to me. For example, if I'm writing a function, I'll talk about functions later. Okay, maybe after 1 or 2 weeks, I'll come back talk about functions in great details. So if I'm writing a function, I'm going to pass the parameters or the arguments in these three registers. So I need a register that will contain the address of the array A. I need a second register for n, the number of elements in the array, and I need a third register A2 for the value that we are searching for. Right now, given these, how do I translate this while loop? Now, remember one thing is that the address of the element at index I, A of I, is the address of A. I probably wrote. Okay, so it's the address of A plus I multiplied by 4. Okay, so that's this is how we calculate the address of A of I. But we can also say, because we are traversing the elements one by one in a linear way, I can say that the address of A of I is the address of A of I minus 1, the address of the previous element plus 4. Okay. Now, this kind of address calculation is essential when you would like to traverse the elements of an array. Now, I'm going to translate this while loop. I'm going to write here a label. This will indicate the beginning of the loop. You can give it any name. We are going to load the value of A of I. So I'm going to start here at the address in A0. Notice that A0 is the address of the array A, and I is initially 0. So this load word is going to load the value of A0 into register T1. Notice that I'm using load word because it's a 4 bytes per element. Okay. So you have to be very careful about these details, okay, when doing the translation. The compiler does it automatically for you, okay, but now we are doing it by hand. We are understanding how the compiler works. So after loading the value of AI, initially I equal to 0, so this will be the value of A0. So we are loading it, okay, from memory into register T1. So I have T1 now is the value of the first element of the array. What do I need to do?
Apply the condition.
Yeah, I need to compare it. I need to compare it against value, right?
Yes.
I need to compare if it is not equal to value. Just 1 second, bear with me. Okay, so we need to compare it against value. So how do I compare it against value?
Branch is equal.
Yeah, so I can actually use a branch instruction to terminate this loop if it is equal, because it says if it is not equal, continue looping, right? So if it is equal to value, so I can use a branch if equal T1, value is A2, register A2 here, okay? That actually is value. Value is stored inside a register, which is register A2. So therefore, we are going to say branch if equal T1, which is the value of AI, is equal to A2. I would like to branch outside the loop. So,
but Doctor, we have.
This is actually we are done. We are done. Khalas, we have terminated the execution of the loop. The value is found, and that's it. Okay, so this is my branch if equal instruction. Yes, Ali. Do you have a question?
Yes, we have and condition. It's I is less than n.
Okay, we have another end condition. So how do I translate this end I is less than n? You tell me.
Because if we want to translate two condition, we can't
So,
jump to done.
So now we
from
use
the
here branch if
first.
equal. So we check if this is false. So not equal, it means equal. So we branch if this is false, we branch, we are done. So there is no need to continue. So what is not I less than n?
Then we translate.
It will be what? We need a
More
second
than
branch
equal?
instruction,
Yeah.
right? We need
Yes,
second, because we have two conditions.
Yeah, if
I more than.
We can use a branch if it is greater than or equal.
Yeah.
Okay. So if I is greater than or equal to n, we can also branch to done, and we are done.
Yes.
But you see that we started at index I equal to 0. Notice that I is an integer. And I plus plus, this will increment I by 1 each iteration. Okay. So for this reason, it's enough to check if it is equal. Because once it becomes equal, then we can terminate. So I can say that also I have another branch if equal. Branch if equal, I here is T0, n is A1. That's actually A1 is the value of n. We are also done. So if I is equal to n, then we have reached the reached the end of the loop. We are also done. Now, if I don't branch here and don't really branch here, it means that these two conditions here, okay, so if this is not false and this is not false, then continue. Then we simply increment I. Okay, so I here is just T0. I just have to add 1 to T0. Okay, so that's how we increment I. But this is not enough. I have to increment I by 1. This is not enough. So this add IU is going to add 1 to T0. So this is going to increment T0. But this add IU is not enough. I need the second add IU. I need the second add IU to calculate the address, because when I look back, I need to have a different address in A0. So I'm going to increment A0 by 4. So I'm going to add 4 to A0 so that we address the next element in the array A. So notice that A0, we started by A0 having the address of the array A. So by now adding 4 to the address, we can now address the next element, okay, in the array A. So now A0 will contain the address of AI. Okay?
Doctor.
Okay.
When we start in the loop, load the word,
Yes.
the register T1, we mentioned the value of I, which is 0, right? Now
right.
I will.
But load word has nothing to do with I.
Yeah.
It has to do with this address, which is in A0. Because in the case of load, what you have to do is that you have to specify the memory address. So load does not really work the same way that you index an array in a high-level programming language. Load needs the address. So you have to address memory. So the address of the array exists in A0. Notice that the immediate is 0 here.
Yes.
So therefore, we started here at the address of the first element in the array. So before we look back, the next element in the array, I have to change A0. I have to point to the next element in the array. So we have to do address calculation. So this address calculation is by increment A0 by 4 to point to the next element in the array. It's not enough to increment the index by 1 because we are not really using T0 here. We are using A0 to address the array. Is this clear?
Yes. Yes, clear.
Okay. So now once we are done with this, now we are ready to start the next iteration. Just jump the loop. So jump the loop, this will jump backwards, and then we will start the next iteration of the loop. And we can continue like this until either the value is found, and we branch here to done, if the value is found, or when I becomes equal to n, it means that we have traversed all the elements of the array, and we are also done. So one of two things can happen. Either the value is found at a given index I, and of course this index has to be between 0 and n-1, or it is not found, then the index becomes n, and we have traversed all the elements, and we are now indexing outside the array, so the index becomes n, then we stop. Okay, we branch to done, we are done, and the value is not found inside the array. Is this clear? So this is an example about how we translate a while loop. I have a second example here, which is about a do-while loop. Now, in the case of a do-while loop, okay, you write the condition at the end of the loop. And here, for example, say do while, and then you write your Boolean expression here. So you have to check this Boolean expression at the end of the do while. Again, as I said, compilers don't really need to understand this code. They will take the code as is in the high-level programming language, and they have to translate it properly into assembly. So the translation is automatic, but we are going to do it by hand. We are going to do this translation by hand. So if you look at this code, what this code is doing is that we are just copying a string, a source string to a target string. Okay, for example, if you would like to write in a C programming language, what you have to do is that you have to copy each byte, each character. A character is just a single byte. So you have your string is an array of characters, an array of bytes, and you are going to copy it character by character or byte by byte. We are going to copy the source string into the target string. So source and target are two different strings, okay? And therefore here the address, A0 is the address of the target and A1 is the address of the source. These must be given to us, okay? For example, if we're writing a function, we can pass these as parameters or arguments to a function. So we have the address of the target, we have the address of the source, and what we are going to do is we are going to copy the target, we are going to copy the source into the target. So we read here, so first we start at index 0. So I'm going to read a single character CH. So this will be just 1 byte of this source array at a given index I. And then I'm going to copy this character into target CH, increment I, okay, at the end of each iteration. And then we check while CH is not equal to the null card. In the C programming language, every string must be terminated with a null card. The null card can be written as \0. It's a control character which marks the end of the string. Okay, so every string must be terminated with a null card. So we stop after reaching the null card. Notice that we copy the null card itself. So we copy the null card and then we check it. Okay, if the last character that we have copied is a null card, then it means that we have to stop this do while loop. Okay. So if the string is empty, is an empty string, it must have the null card. So an empty string must have at least one character, which is the null card. Okay. So the null card is not really printed, it's not really shown inside the double quotes, but it always marks the end of the string. Now, in some programming languages today, very high-level programming languages, what they do is that you can do this with an assignment. You can just assign one string to another string. But really, the string is an array, and you are just copying the characters of this array, character by character. Okay, so it becomes a loop. So even though in some high-level programming languages they hide these details, okay, but really in assembly nothing is hidden. Everything becomes clear because this is how the CPU works. You have to see, basically, you have to write a loop that will copy the string character by character. So let us do it quickly. So I'm going to start by initializing I to 0 and start here by reading. Now, what is here CH equal to source I? The first statement. What shall I do? CH becomes source I. This is a load. This is a load.
Yes, load.
So we have to load 1 byte. Now notice it's an array of characters. So it's an array of bytes. So you have to use the proper instruction. You have to use load byte. What is this? What is the target I becomes CH? The second state inside the loop.
Store.
It's a store. Yes, it is a store. Okay. So first you have to load, then you have to store, then you have to increment the index, and then you have to check this condition. So let us do it. I'm going to write a loop. Now notice that I'm going to use load byte here to load from this address A1. A1 here is the address of the source string. Put the value in T0. So this is going to load 1 byte, 1 character of the string into T0. Then I'm going to use store byte to store this character in memory at the address of A0. So A0 here is the address of the target. So we load a byte from the source string into T0, and we store this byte or this character. We store it in memory at the address of the target string. So we did here CH equal to source I, target I becomes CH. Now I need to change my pointers. I'm doing it slightly differently than the way it's written in the high-level programming language. Notice that I'm not using an index. I'm using here A1 and A0 as memory addresses. So what we need to do is that we need to advance the address. So I'm going to use this add immediate to advance the address in A0. This will actually advance the address of target. So this will point to the next character in the target string. And I'm going to use another add immediate to change the address in A1. This will point to the next character in the source string. So notice that A0 and A1 contain memory addresses. And we are going to branch. Notice that the branch is not equal to 0 because here it says CH. So CH is the value which is loaded into register T0. So we branch if this T0 is not equal to 0, because character here, the null car has a value of 0. So if it's not equal to 0, okay, we still have more characters to copy. We branch back to loop. Notice that the branch appears at the end of the loop. So we write the branch at the end of the loop because it's a do while statement. So the condition is checked at the end of the loop. Notice that the do while will have to execute at least one iteration because the condition is checked after executing the body of the loop.
Doctor,
Further.
when you use the branch not equal to 0, isn't it really 0? Number
Yes.
0?
Yes.
Because
yes.
here
the character itself is encoded as the number 0. Remember that each character has a code, and this code is just an integer. And the character 0 or the null car, this is not the digit 0. This is the null car. Okay, this is a control character. It's \0 because the digit 0 has a different code. Okay, so there is a big difference between the digit 0 and the null car. This is the null car, and it's encoded in binary as 0.
Yeah, I got.
Okay.
So
good.
we want to branch. For example, if we want to branch, if it equal to digit 0, we will not use branch not equal 0. We will use something different.
Yes, you are right. So what we have to do is that we have to have the character code in a register, and then we can say branch not equal to this
not
code.
Not equal, yeah.
We can use branch not equal, and we have to specify the character in a different register, and we have to compare two registers.
Okay.
You are right. We have seen two examples. I would like to show you now a third example about a matrix. So in this example, suppose I would like to write a loop that is going to initialize a column of a matrix. So in this example, I'm using the column at index 3. Notice that I changes. Okay, so I is my index, it's my row index, my column index is fixed at 3. So initially, we are going to allocate the matrix. I'm going to allocate the matrix dynamically. I'm just using here my own syntax. Of course, you can use the new operator in many high-level programming languages to allocate arrays dynamically on the heap. So I would like to allocate here an array of integers, a two-dimensional array with 10 rows and 5 columns. So if you multiply 10 by 5, these will be 50 elements, right? And if you multiply each element by 4 bytes, because here an integer is 4 bytes, then you need to allocate 200 bytes. 200 bytes, a block of 200 bytes for this matrix. So at a low level, okay, so the matrix is just a block of bytes in memory, and we can use the system call to allocate the matrix on the heap at runtime. So this is not static allocation, this is dynamic memory allocation in this example. Notice that for address calculation, in order to initialize this column of the matrix, so here I have MI3. We need to write to this element in the matrix. We need to do address calculation. And in order to calculate the address, this is the address operator. In order to calculate the address of MI3, I need the address of the matrix M in memory. This will be the base address. And then I need to multiply the row index I by 5. Now I need to multiply it by 5 because I have 5 is the number of elements. This is the number of columns in the matrix, which is the number of elements in each row. Okay, so the number of columns here, it means the row length, how many elements you have in each row. So we need to multiply I by 5 and add to it plus 3. This is the column index. So this will tell me how many elements to skip before reaching this element inside the matrix, but each element is 4 bytes, so I have to multiply everything by 4. Now, if I expand, it will be I multiplied by 5 multiplied by 4. This will be I multiplied by 20. And then I have here 3 multiplied by 4. This will be 12. So the idea, so we need to do this kind of address calculation in order to generate the memory addresses at when we write the code in assembly. We need to do address calculation. So it's very important to understand how we generate the address of this element inside the matrix. If you have any question about this, just feel free to interrupt me. So just go back to the previous slide where I described the address calculation, okay, for the matrix elements. So this is the address of MI3. I'm going to use it, okay, in the programming. So the first step is to allocate the matrix on the heap dynamically. We need 200 elements. Sorry, we need 200 bytes. We have 50 elements. 10 rows multiplied by 5 columns. These are 50 multiplied by 4 bytes because we are dealing with a matrix of integers. So 200 bytes. So you have to specify the number of bytes. So we initialize A0 with 200. And I'm going to use system call number 9. So this is why I have to initialize B0 with 9. And this is the system call that is going to allocate 200 bytes on the heap. So it's going to allocate whatever number of bytes that you specify in A0. And we are doing this allocation dynamically. So once the system call is executed by the program, and it can be done in any instruction in your program at any point in time, then the dynamic memory allocation will take place. So this will be in the dynamic area in the data segment. So these 3 instructions are going to allocate the matrix dynamically. It is just a block of bytes. Now the result of this system call will be the address of the matrix. So once we finish the execution of this system call, okay, so the system call is going to transfer the operation to the operating system that does the memory management is going to allocate the matrix dynamically at runtime. These are details how this is done by the operating system. We're not going to these details. So once this is returned, so once we return from this system call and we move to the next instruction, V0 will contain the address. So the system call is going to return the address of the matrix in V0. So I'm going to move the value of V0 into T0, okay, because I need this address, the address of the matrix. So the address of the matrix will be in register T0. You can, of course, copy it to any register. Here I'm using T0. So now we have the matrix in memory, and we have the base address. So we have 200 bytes that were allocated, and we have the address of the matrix in T0. What I need to do is that I need to write this for loop. I need to initialize I to 0. Okay. Now, rather than using the index, we need to calculate the address. Okay, because I'm saying that mi3 is equal to I. So I need this index I, but I need also the address of the element, the address of mi3. And I have a comment here on top that shows how we do the address calculation. So it's the address of m, which is already in T0. Now we have to take this index and multiply it by 20, and then we have to add to it 12. Now the address of m is always in T0. Now inside this loop, we're going to increment, so we're going to start from index 0 to index 9. Okay, so I here is strictly less than 10, so we only have 10 rows inside this matrix. So these are the 10 elements inside this column of the matrix. So we need to initialize these 10 elements. In order to do this, what we need to do is that we need to store the value. So we need a store instruction here, a store word, because we are writing to memory. The matrix exists in memory, and we need to write to memory. And I need only to initialize one column of the matrix. Okay, is this clear? So this is what I need to do. I need to write the instructions now. Okay, I need to write a loop. I need to write the instructions for this for loop. And I know that I'm going to loop 10 times, 10 iterations. And the index I is going to go from 0 to 9. So here M03 will be 0, M13 will be 1, and so on. Is this clear?
Yes.
Now, can you tell me how this should be done?
I'm just confused. The MI at the column
so
3.
This appears on the left-hand side of the assignment operator. Remember that I'm going to use my pen tool now. Okay, so this MI3 appears on the left-hand side of the assignment operator. This is my assignment operator, which is shown here, right?
Yes.
So when I assign, I'm assigning here, I'm writing to MI3.
So we need to load.
But this matrix exists in memory. So therefore, I have to use the store instruction to store the value of I in memory. And of course, I is changing. Okay, I is changing in the loop. So each iteration, we have a different value of I. Okay. So I need to use the store word instruction because I'm storing here an integer because each element is an integer. So store word, and I need to have a different value of I. I can use a register here to initialize I to 0. I can use any register for that purpose. And then I can increment I++ at the end of each iteration. But what's important is to calculate the address of MI3. Now, initially, when I equal to 0, the first iteration I equal to 0, it will be the address of M plus 12. So you can see that here plus 12 here is my what? Is my displacement. Okay, so I need to have a displacement which is equal to 12 bytes. So initially, when I equal to 0, it will be the address of M plus 12. But then when I increment I becomes 1, I need to add 20. 1 times 20 is 20. So every iteration, I have to increment the address by 20 bytes to calculate the address of the next element in my column. Okay. If I want to draw my matrix, okay, I can draw my matrix here. Oh, I need, just give me a second. So let me draw my matrix here. So I'm going to use my touch screen to draw my matrix. So sorry, I don't know what I did. Let me just go back here. Oops. Let me escape this. So now let me draw my matrix here. So in order to solve such a problem, you need to do address calculation. You have to think about your matrix in memory. So this is column 0, this is 1, this is 2, this is 3, this is 4. We only have, okay, these 5 columns. You can see the 5 here, right? So I need to initialize this column 3. And of course, the rows are 0, 1, 2, etc., up to row 9, because we have 10 rows in total. So this is my matrix in memory. So initially, I'm going to initialize this element here. This will be M03. Then this will be M13. Then this is M23. And the last element in this column will be M93. Now notice that because we have only 5 elements in each row, to reach the next element, if I know the address of this element here, okay, so let me write it down. Okay, so this is the address of M03. If you would like to calculate the address of M03, according to this equation that we have seen here on top, it will be the address of M plus 12. Okay, because I is equal to 0. The index I equal to 0, so we just add 12. Now, if you would like to calculate the address of this element here, which is M13, it will be the address of M03 plus 20. So to calculate the address of M13, we need to add 20 to the address of M03. Why? Because we have 20 bytes in each row. We have 5 elements. Each element is 4 bytes. So we have 20 bytes in each row. So now what I need to do is I need to write this loop. So let us take a look here at the code. So first I'm going to initialize I to 0. Okay, this is my index I. I'm going to use T1 here for the index I. Let me use my highlighter. So T1, it's very important to write comments to explain what you are doing in assembly. So things in assembly are really more low level, okay, than when you are programming in a high level programming language. So you have to show these details. So this T1 is my index I. I'm initializing it with 0. Now T2 here is 10. If you would like, this is the number of iterations because we are going to repeat 10 times. Now I'm going to start entering my for loop. So my loop starts here at this table, which is L. The first step is to store M03. So initially I'm going to use here T0. T0 is the address of M. So this is the address of M plus 12. So I'm going to store the value of T1. T1 is basically the index I. Okay, so I'm going to store here T1 at this address. You notice that the instruction is a store word because we are writing to memory. I'm going to increment the index I by 1. So this is add IU. So this is going to increment the index by 1. And also, I'm going to change this address in T0 by 20. Another add IU that will increment the address by 20 bytes. So that when we look back here, okay, we store another element at the address. So we start initially here at the address of M03, then this will be the address of M13. So the address of M13 is equal to M03 plus 20. So we need to increment the address by 20. So each iteration, we add 20 to the address of the previous element in the column to calculate the address of the next element in the column. And then we branch if T1, if the index I is not equal to 10. So branch not equal, okay, and we look back. After we have finished 10 iterations, we are done, okay? So that's it. This is how we initialize a column of a matrix. Any question about this example?
Doctor, an integer is 4 bytes?
Yes. The type int is 4 bytes. So when you would like to allocate an array of integers, each element of the array will be 4 bytes. Yes.
Okay.
If you have an array of characters, okay, then each character will be just 1 byte if it's an ASCII character. Okay. If you are dealing an array with half words, then each element, for example, if you are dealing in a high-level programming language with the short integers, but you have the type short, right? So if you are dealing with short integers, then each element will be 2 bytes in memory. Any other question?
Doctor,
Yes,
is
Sam.
it possible that integers can be byte?
Each integer is 4 bytes. So one integer is 4 consecutive bytes in memory. So when you would like to load an integer, you have to use load word. And when you would like to store an integer in memory, you have to use store word. Word is equal to 4 bytes. You are reading 4 bytes, you are writing 4 bytes. Okay, it's not just a single byte, but it's 4 bytes. Even though the integer is a small, even the value, for example, if it can fit, even if it can fit in a single byte, you are going to write 4 bytes in memory. Okay, so the size of the integer is always 4 bytes, regardless of its value. Is this clear?
Yes.
Okay. Fine. Let us continue. Let me conclude, okay, my presentation here with the addressing modes. So what I mean here by addressing is where are the operands and how memory addresses are computed. Already we have seen these things, but I need to summarize, okay, the concept of addressing modes, okay, in the next few slides. So first we have immediate addressing. So when I say immediate, it means that we have a constant as part of the instruction. So here we are using the I-type format, and we have the immediate, which is a constant part of the instruction. So we call it immediate addressing. Okay, and you have one operand is a constant. Okay, only one of them. So RS is my source register, and my second operand is a constant, and RT is my destination register. For example, when I'm doing add immediate or end immediate or immediate, all of these instructions use a 16-bit immediate. So we call this immediate addressing. On the other hand, register addressing, we are using the R-type format. We have 2 source registers, RS and RT. So we read 2, and we write 1 register, which is RD. Okay, I noticed that some of you in the quiz 2, they don't write the destination register. Okay, so you have to write the destination. So you have to write 3 registers, not only 2. So you have 2 source and 1 destination. So this will be register addressing. So we are reading 2 registers and we are writing a register. Okay, so the operands are in registers. Now notice that in the case of immediate type, we also have registers here. Okay, but we also have a 16-bit immediate. So we are reading 1 operand from a register, and the second operand we are reading it, we have it as part of the instruction as a 16-bit immediate. But in the case of register addressing, all my operands are in registers. In the case of load and store, in the case of load and store, we use the base displacement addressing. So my operand here exists in memory. Yani, for example, you can have an array or a string which is in memory, and the element can be a single byte. Each element of the array can be a byte, or it could be a half word, or it could be a word. Notice that half word is 2 bytes, and word means 4 bytes. Okay, so we do here base displacement addressing. So in the case of load or store, the register RS will contain the base address, and the displacement is the 16-bit immediate. So what the CPU will do is going to add, okay, the value of register RS plus the 16-bit immediate to calculate the memory address. So this type of addressing is done by load and by store instructions. Okay, and this is memory addressing because we are reading or writing memory. So this is load and store. Okay. We also have, okay, branch and the jump instructions that also address memory, but rather than addressing data, we are addressing instructions because the instructions of the program also exist in memory. So when we fetch and execute instructions, the program counter contains the address of the instruction that should be fetched. So in the case of a branch instruction, the branch is also of the immediate type. So we have a branch if equal, branch not equal. So here RS and RT are both source registers. So we read RS, we read RT. We don't write RT, we read it. And we can use these two. So we compare these two values. We can check them if they are equal or not equal. And then we branch accordingly. So if the branch is taken, okay, what we have to do is that we have to look at the current value of the PC. The current value of the PC is the address of the branch instruction itself in memory. We add to it the 16-bit immediate, but the 16-bit immediate is added to the upper 30 bits. The least significant 2 bits of the PC are always 0, 0, because the address is always multiple of 4, because the instruction is 4 bytes in memory, and all the instructions are aligned in memory. So therefore, their addresses are multiple of 4. So when you look at the number in binary and the least significant 2 bits are 0, 0, it means that this number or this address is always multiple of 4 bytes. So we take the 16-bit offset, we add it to the upper 30 bits. I'm showing here PC 30. These are the upper 30 bits. Plus the 16-bit offset. This is the 16-bit immediate that exists inside the instruction, plus 1. Now, plus 1, because PC 30 plus 1 will be the address of the next instruction. So we call it PC relative addressing. Okay, PC relative addressing. And this is how we calculate the branch target address. So once we have calculated the branch target address, we update the PC and we branch to the instruction. Okay, so this is my target instruction. So remember that the instruction itself is a word, is 4 bytes in memory, like an integer, okay? But it is an instruction. So it occupies 4 bytes. And we need to calculate the address, okay? So this is what we call the branch target address. So this is done by the CPU at runtime. So if the branch is taken, then this will be the branch target address, okay? In the case of a jump, it uses a slightly different addressing mode. In the case of a jump instruction, which is called pseudo-direct addressing, this is how it is defined in the MIPS architecture. So in the case of a jump, there are no registers. There is only an opcode, and there is a 26-bit address. So this is a 26-bit constant and immediate, which is part of the instruction, and this specifies the address. So what the jump instruction does is going to modify 26 bits inside the PC register, and this is what we call the jump target address. So you can modify any one of these 26 bits. Remember that the least significant 2 bits are always 0, 0, because the address of an instruction is always multiple of 4. Okay, So this is how we address instructions so this is how the jump instruction addresses instruction in memory. This is how it calculates the jump target address. Okay. So branch and jump only modify the PC register. They don't modify any other register inside the hardware. It's only the program counter register which is modified. Now, there are limits for the jump and branch instructions. How far we can jump, how far we can branch. In the case of a jump instruction, we define the jump address boundary is equal to the power 26 instructions, because we are using a 26-bit address inside the instruction. And these 26 bits can be any value, okay, between 0 and 2 to the power 26 minus 1. So therefore, you have 2 to the power 26 possible binary values. And these can be used to address 2 to the power 26 different instructions in the same segment of memory. Okay. Now, if you multiply 2 to the power 26 by 4 bytes, you get 2 to the power 28 or 256 megabytes. So this is the size of the text segment, or this is the size of the segment that can be reached by the jump instruction. Okay. The upper 4 bits of the PC will be unchanged. So therefore, this is the limit of the jump instruction, how far we can jump in memory. So we cannot reach outside this 256 megabyte segment. So this is the boundary of the jump, because we are only using a 26-bit address inside the jump instruction. In the case of a branch, we are using only a 16-bit offset, because it's of the immediate type. And when we branch, we calculate the PC relative address as the upper 30 bits of the PC plus the 16-bit offset plus 1. And this is how we can calculate it like this. So the 0, 0 here at the end, it means that we are multiplying by 4, and we are adding it. We are adding offset plus 1 multiplied by 4. So this is the branch target address in the case of a branch instruction. So you can think about the offset here as counting the number of instructions to skip. This is the meaning of the offset, counting the number of instructions to skip. But we don't start at the branch, we start at the next instruction, because we are adding 1 to the offset. So by adding 1, this will be the address of the next instruction in now. Okay. So therefore, we count the number of instructions to skip starting at the next instruction, because if we don't branch, we just go to the next instruction in memory. Now, this offset can be positive or it can be negative. If you use a positive offset, it means that we are incrementing the PC, and therefore this will be a forward branch. We are branching forward. If we use a negative offset, it means that we are branching backward. Like in the case of a loop, when I would like to branch, I have the branch at the end of the loop, and I would like to branch to the beginning of the loop. So this will be a backward branch. Now, because we have 16 bits and the offset is signed, it can be positive or negative. So we can say that at most plus or minus 2 to the power 15 instructions can be skipped. So this is the boundary. That's how far we can branch. Okay, so we can skip 2 to the power 15 instructions forward as well as backward. Okay, so that's how far we can branch in memory. But this is sufficient. This is sufficient in most programs. You don't really have to branch that far. So when you are dealing with loops or if statements, the branch is near, the branch target instruction is near, and therefore we don't really need to branch too far. And the 16-bit offset in the branch instruction is sufficient for most branches. If you would like to branch beyond this, you can branch to an instruction, and this instruction can jump, that can take you even beyond this limit. But normally, as I said, that in most programs, people found that programmers found that there is no need to branch that far. And this is why the 16-bit offset is good enough in most programs. But if you would like to branch even beyond this, there are tricks that you can do in programming. So you can branch to an instruction, and this instruction can be a jump that can take you even beyond this. Okay? Any question about this? So these are the jump and the branch limits, which are related to how many bits we are using inside the instruction to define the branch offset or the 26-bit address in the jump instruction that will tell you how far you can jump. Okay?
Doctor?
Yes.
The last thing you said, most branches are near. What does that mean?
It means that if you are writing an if statement and you would like to branch, you would like to skip, you are not going to actually to skip 1 million instructions. You are probably going to skip maybe 10, 100, maybe 1,000 instructions. Okay? So therefore, when you write your label, when you would like to branch this label is not very far in your program. That's what I mean.
Okay.
Okay, so for this reason, the offset is not going to be very, very large. Okay, and for this reason, it can fit in 16 bits.
Victor, I have a question.
Oh.
For the PC relative addressing, we take the current PC address and we add the offset to it. But in the jump target address, we did not add the current PC address to the 26-bit address. We just
so we have
the upper 4 bits.
Okay, yeah. So if we would like to, so we have two different addressing modes for a branch and for a jump. Okay, if I would like to go back here to my previous slide. Okay, so in the case of the branch of the immediate type and uses a 16-bit offset. So we are saying that PC is equal to PC plus, okay, we add 1 to the offset and multiply it by 4. We multiply it by 4 because each instruction is 4 bytes. And this is actually because we have the least significant 2 bits of the PC are always 0, 0. Okay. So this is PC relative addressing. So remember that the offset is only 16 bits in the case of a branch, whereas in the case of the jump, the address is 26 bits. It's longer. Okay. So you have 10 extra bits. Here you only have 16 bits. Here you have 26 bits. And the addressing mode is different. The way that we calculate the jump target address is different from the way that we calculate the branch target address. Here we have to look at the old value of PC and add to it a number, whereas here we change 26 bits directly inside the PC itself to calculate the jump target address where we would like to jump. Now this means that you can jump far in the case of a jump instruction within a segment that contains 2 to the power 26 instructions or 256 megabytes, whereas in the case of the branch, you cannot branch that far. You can only branch plus or minus 2 to the power 15 instructions because we are only using a 16-bit offset that can be signed, positive and negative. So if you would like to think about them, half of these offsets will be negative and half of the values will be negative, and we have half of them will be 0 or positive. Okay. Is this clear? So this will tell you the limit, how far you can jump and how far you can branch. In terms of programming, this is good enough. This is really excellent. Okay, because in most situations, in most programs, you don't need to branch very far or you don't need to jump very far. Okay, so the jump is near and the branch is near. The label where you would like the target of the jump or the target of the branch is near. Okay. Questions? So this is a summary of RISC design. We have seen that in the case of the MIPS architecture, not only the, by the way, we have seen not only the MIPS architecture, but in fact, there are many architectures like MIPS, the ARM architecture, okay, which is more popular than the Intel architecture. And it is used on inside all phones today. And when you buy a cell phone, the CPU inside the cell phone is an ARM processor, which is very similar to the MIPS architecture. And if you would like to go and see the details, you will understand it very easily, the ARM architecture, because it's very similar to MIPS. Maybe the formats are slightly more complex, but all the instructions are of the same size. All the instructions are 32 bits. There is no exception, okay? And this is very nice because you can have each instruction 4 bytes in memory, and all the instructions are aligned in memory, and their addresses are multiple of 4. So this will simplify the hardware implementation. When the CPU wants to fetch and execute instructions, okay, it knows that all the instructions occupy 4 bytes in memory. So this will simplify their fetching, their decoding, and so on. There are few instruction formats. The upper 6 bits were always the opcode. So this will simplify the decoding of these instructions. And of course, the opcode will tell you whether you have an R type or an immediate type or a jump type, okay, based on the opcode itself. Okay, so this will simplify really the implementation of these instructions inside the CPU. We have seen that all the arithmetic and logic operations are register to register. We read 2 registers, we write 1. And in the case of, let us say, when we have let us say an immediate constant, we can use the immediate type. We can have the second operand as an immediate. The first operand will be the value of a register. The second can be an immediate constant, which is part of the instruction. And we write the result to a register. We use general purpose registers. And we have seen that we have 32 from register 0 to register 31. So these are 32 in total. But one of them, which is register 0, is always 0. It's hardwired to 0 because it helps in the programming. So it simplifies programming. And for this reason, the designers of the MIPS architecture, they thought, why not dedicate a register, which is always 0, to simplify programming. So if we use registers, registers are really faster than memory, because you can, let us say, operate on registers. You can do arithmetic on registers much faster. You can read and write registers inside the CPU much faster than loading and storing memory. Okay? If you want to access memory, you have to use the load and store instructions. So this is why it's called a load store architecture, because the only instructions that access memory are load and store. But you have many of these instructions. You can load a byte, you can load a half word, which is 2 bytes, or you can load a word. And there are also instructions that allow you to load a double word. Okay, not just 1 word, but double word, which means 8 bytes. And you can load it into a pair of registers. And there are a few simple addressing modes. So this is just a summary of the RISC design. It's simple, it's elegant. You can have really very simple implementation of these instructions in the hardware.